In this video, we are going to finish up section 14.3. This was double integrals using polar coordinates. So we have this problem. It's going to change just a bit. They say find the volume between two surfaces. And it's very hard to tell what those surfaces are. Here, maybe you can tell that's just going to be a plane. So we have that. We could try to think about that, but the best way to do this, because surfaces are very hard to imagine, is if I want to know, if I have two surfaces and they want the volume between it, that means that it's enclosed. That means they intersect. It means I got to have something like this, like two parabolas with some kind of closed area, right, but in 3 dimensions. So I would be very interested in this case where they would intersect, like we did in Calc 2. So to do that, all we have to do is set our two surfaces equal to each other. They're both equal to z, so I'm going to go ahead and just set them equal to each other. And we solve. I'm going to minus 1, so I got 8 on the left, and then I'm going to add those over. And then dividing everything by 2, we have x squared plus y squared equals 4, right? And hopefully you can tell what that is. I'm going to go to polar just in case you can't. X squared plus y squared is r squared, which means r is 2. All right, so we're dealing with some kind of intersection in space of a circle with radius 2. So here's my circle. Just going to do this to make it easy. There is my circle, radius 2. I can fix all this. All right, so I know this is my xy plane, and I have those two surfaces above it, and I know that that's where they're going to intersect. So I need to run my integral now. Right, it's circular, so this tells me that the volume would be probably best found using polar. We are finding everything inside, so it's all this in here, right? The volume of everything above that in this surface. So if it's all the way around, we know that in polar we use thetas, and theta always goes on the outside the last, and it's going all the way around, so 0 to 2 pi. And then the radius, how we tell, is we start at the origin. I just go straight out from the origin there. So it's going to be r equals 0 to r equals 2. We always just start inside and run an arrow out. And we always start, this will be our bottom curve, and then I put a 0 up there, but it should be a 2. And then the second curve it hits is the circle. All right, then I have my surface. Now my surface is going to be the top minus the bottom. If you're wondering on how to figure out which one's top and which one's bottom, you could plug in a number. I know z is always going to be 1. And then I could put, I know 0, 0 is in there. So if I plug in 0, 0 to this function, I get 9. So this is the top. This is the bottom. So if I subtract the 2, that's what's going in here. So I got 9 minus 2x squared minus 2y squared minus 1. Right? You could have also just had the equation, this equation set equal to 0 would also do it. And then we have r, we haven't converted yet, but we have r dr d theta. And then now we can convert that. Okay, well, this becomes 8 minus 2x squared plus y squared. Which tells me, all right, so I have theta from 0 to 2 pi. And then r equals 0 to r equals 2. And then this becomes 8 minus r squared. 2r squared. Just lost the 2 there. And then r dr d theta. Careful with that r being multiplied by everything inside. All right, so now we can actually evaluate our integral. Okay, so I got theta from 0 to 2 pi. R equals 0 to 2. And then I'm going to multiply. Let's multiply this out up here and save us a whole step. I got 8r minus 2r cubed. So if I run that integral, all right, we raise it by 1, divide by the new one. So up to 2, divide by, I got 4r squared minus, okay, that one goes up by 1, divided by the new one, I get a 1/2 r to the 4th. Oh, if we already did our integral, we can drop this. All right, so I have that, and we're running this from 0 to 2, d theta. Okay, so if I plug all that in, the zeros are going to go away. If I plug in 2, I get 2 squared, which is 4. 4 times 4 is 16. Minus, if I plug a 2 in there, 2 is 16 minus 8, I get 8. All right, so the integral's still there, though. Theta equals 0 to 2 pi. And I just have an 8 now on the inside. All right, that's an easy integral. This is just going to be 8 theta, ran from 0 to 2 pi, which is going to leave us with 16 pi. So that is the volume caught between those two surfaces. The hardest part about these, I believe, anyways, is setting them up. But it's the same thing. It's top minus bottom. It's the same thing that you're used to. The big mistake here is people forget that R. I'm going to work it out because it'll still work out, and you won't be able to tell until you see that you get the wrong answer.